This lecture continues centripetal force. Let's immediately take a look at the next problem. The next problem involves a rather popular carnival ride that you may be familiar with. This ride is referred to as the Rotor Ride. Basically what this ride consists of is a cylindrical room. You walk into the room, you stand up against the wall, ultimately then the room spins up to uniform circular motion, and then the floor drops. We want to examine that problem in detail. I'm also going to introduce you to the idea of what is called centrifugal force in the context of doing so. Okay, let me go ahead and read the problem to you. Make sure that you copy it into your notes. Okay, a rotor ride, as it's usually called, at an amusement park has a radius of 1.5 meters. Typically, the coefficient of static friction between the rubber wall and a person's clothing is about 0.6. What is the minimum period necessary such that a rider does not slip, and how many G's of acceleration does the rider experience? One of the aspects of this ride that we'll explore towards the later portion of the problem is we'll exactly understand why a ride like this is somewhat uncomfortable. Okay, now if you're not familiar with the ride, here's basically what it consists of. Okay, I'm going to go ahead and draw a cylinder here in profile. That is from the side, like so. Okay, and then right here we'll say is the axis of rotation of the cylinder, and it then spins up in this direction, we'll say in uniform circular motion. Okay, now the axis of rotation, like so, is positioned through the geometrical center of the cylinder. If the axis of rotation was not in the center of the cylinder, I wouldn't get on that ride. Okay, then we're given the radius here. The radius of the circle, like so, is 1.5 meters. And the coefficient of static friction between the person's clothing and the wall behind is 0.6. These are typical numbers, by the way, for a ride like this. Okay, and then right here is a rider inside the ride, and the floor has dropped. The person has a centripetal acceleration vector, a sub c, like so, inwards towards the center of the circle, which is over here. Okay, now we just add up the forces using F equals ma. So first of all, vertically, we have the following. We, of course, have the person's weight, mg, straight downwards. And then static friction prevents the person from sliding down the wall. Therefore, the force of static friction has to oppose that, and it points upwards. We're going to set up and solve the problem such that we assume that static friction is at its maximum value. This will then allow us to calculate the period of the rotation necessary such that the riders do not slip. Okay, so right here, like so, is Fs max. And then the question is this: which force in this direction, like so, is causing the centripetal acceleration vector inwards towards the center of the circle? That's the normal force, because after all, the person is against the surface like so, so then therefore the normal force pushes in this direction. Okay, now let's just add up the forces using F equals ma. Okay, vertically there's no acceleration, so everything cancels. We have Fs max is equal to mg. And then in the radial direction, we have the normal force vector here pointing in the same direction as A, so N equals ma, mv squared over r, like so. Okay, now before I proceed further into the problem, let me pause at this moment. Throughout this unit on dynamics, beginning, for example, at the beginning of chapter 4, we've always been setting up and solving these problems involving F equals ma from a specific type of reference frame, a specific type of point of view. This is from the point of view of what is called an inertial reference frame. Okay, an inertial reference frame is a reference frame that is at a constant velocity, usually just simply assumed to be zero. So imagine an inertial reference frame in the context of this problem in the following manner. It's as if we're sitting here in this classroom, watching the ride then rotate here on the board, and we then describe the forces that we see acting on the person. In other words, from our point of view, we are at rest. So then therefore think of us as an inertial reference frame with a constant velocity of zero. Okay, so once again, an inertial reference frame is a reference frame at a constant velocity. Usually treated as being at rest for simplicity. Okay, it's as if we're at rest here in this classroom watching the problem occur on the board, and then we describe the forces, blah, blah, blah. That's from the point of view of what is called an inertial reference frame. But now I want to turn the problem around. Now I want to describe the problem according to a person inside the ride. From that point of view, we have what is referred to as a non-inertial reference frame. A non-inertial reference frame is a reference frame that is accelerating. In this case, the rotating room itself. There's a centripetal acceleration inwards towards the center of the circle. However, if we think of the rotating room as a reference frame, it's what's called a non-inertial reference frame. Okay, let me describe this here on the lower board. Okay, so non-inertial reference frame. This is a reference frame that is accelerating. So now, from the point of view of the rider inside the ride, let's describe the forces. Okay, draw upon your own experience. For those of you that have ridden a ride like this, basically what forces do you feel? Okay, well, first of all, we still have, for example, the force of gravity straight downwards. We still have static friction at its maximum value preventing you from slipping. And then we still have the normal force like so inwards towards the center of the circle. But what else do you feel inside the ride? You feel something pulling you away from the center of the circle. That's what's referred to as the centrifugal force. Okay, now let me ask you this. Is there actually anything physically there pulling you away from the center of the circle? No. So for that reason, the centrifugal force is an example of what is called a fictitious force. Fictitious forces arise in non-inertial reference frames. Okay, now what causes the centrifugal force? What causes the centrifugal force is two things. Number one, the fact that you have inertia. So if I go back up to the top board for just a moment, let's say that this is you inside the ride, and at this moment your velocity vector is in this direction out of the board. So you have inertia, a tendency to remain in motion like so. However, secondly, we also have the fact that the room itself is rotating like so, about the axis of rotation. So the combination of your inertia and the fact that you're in a rotating room, this ultimately then means that from your point of view, in the non-inertial reference frame, you feel a fictitious force, in this case pulling you away from the center of the circle. That's what's called the centrifugal force. Okay, so summarizing that briefly here, the centrifugal force is an example of a fictitious force. Fictitious forces arise in non-inertial reference frames. Okay, it's caused by your inertia and the fact that you're in a rotating reference frame, assuming that you're the passenger or the rider in this ride. Make sure that you copy this important information down in your notes. Okay, let me give you a few other examples of fictitious forces that arise in non-inertial reference frames. So go back to my qualitative lecture on inertia at the beginning of this unit. And then we looked at a couple of conceptual situations involving a car. So imagine being in a car, and a car isn't traveling down the freeway at a constant velocity, it's a constant speed in a straight line. And then the driver applies the brakes to the car. And then you keep going forwards because of the fact that you have inertia. Something that is a force has to be exerted upon you, causing you to slow down, your seatbelt, for example. However, now think of the car as it slows down as a reference frame. So then therefore it's a non-inertial reference frame because its velocity is decreasing, it has an acceleration. So then therefore from your point of view, you feel something pulling you forwards, you feel a fictitious force. There's nothing physically there pulling you forwards. You feel the fictitious force because you have inertia, and secondly, you're in a car that is slowing down. You're in an accelerating reference frame. Another example of a fictitious force. Still with a car, here's another example that we looked at also in my qualitative lecture on inertia. So let's say that the car is initially at rest, and then the driver applies the accelerator to the car, and the car accelerates forwards. And then what happens to you inside the car? Well, from your point of view, you feel yourself get pulled backwards. Okay, now remember that ultimately you are just remaining at rest relative to the ground until something pushes you. But now picture the situation from your point of view inside the car. It's a non-inertial reference frame. So then therefore you feel a fictitious force pulling you backwards. Once again, there's nothing actually there. You're just feeling a combination of your inertia and the fact that the car is an accelerating reference frame. Here's another example. The surface of the rotating Earth. When you stand on the surface of the rotating Earth, you do have a centripetal acceleration inwards towards the axis of rotation. So then therefore, do we now feel a fictitious force here at the surface of the Earth? Yes, and here's how it works. Okay, I'm going to have to recopy this diagram when I return to the problem in a few minutes, but for now, let me go ahead and erase here. Okay, and then let's say right here is a side view of the Earth. So right here is the Earth's equator, like so. Here's the North Pole, and then here's the South Pole. And let's say that we're standing here in Los Angeles, like so. Here's north, and here's south. By the way, as I face my camera here in this classroom, that direction is north, and that direction is south. Okay, and then as the Earth rotates, right here, this circle that is parallel to the Earth's equator, this right here is referred to as our parallel of latitude. And then let me go ahead right here and draw in the axis of rotation like so. So as the Earth rotates from an inertial reference frame, if you were off the Earth and watching the person just rotate around, this person right here has a centripetal acceleration inwards towards the center of the circle. Notice that's not straight down towards the center of the Earth. It's towards the north like so, inwards towards the center of the circle of our parallel of latitude. Here in this classroom, that's roughly in this direction like so. When I point in this direction, I'm pointing towards the north, in this direction like so, inwards towards the axis of rotation. That's basically in this direction. So then therefore, as the Earth rotates, we are actually in a non-inertial reference frame. So you feel a fictitious centrifugal force away from the center of that circle. That's in this direction like so, towards the south. So then therefore, if I take an object and drop it as a projectile like so, it actually doesn't quite fall exactly straight downwards. It actually drifts a little bit to the south. The amount of drift, however, to the south is next to nothing. You're never going to notice it with your senses because the Earth's rotation is rather slight. However, it is measurable. If I do take the marker, for example, and drop it like so, it actually drifts to the south by about 1/10 of a degree or so, and it is measurable. The first time that the Earth's rotation was actually physically detected by physically detecting that fictitious force was in the 19th century with a very famous experiment involving a type of pendulum. This is referred to, this experiment that is, as Foucault's pendulum. Foucault's pendulum is a specific demonstration or experiment, if you will. It was first done in the 19th century. And it's the first physical detection of the Earth's rotation. In other words, the experiment itself, it physically detects the fictitious force that's being exerted on the pendulum from the non-inertial reference frame's point of view. There's a nice example of Foucault's pendulum here in Los Angeles. I'm sure that a number of you have seen it. At what museum do they have a nice example of Foucault's pendulum? In the lobby of Griffith Observatory at Griffith Park. That huge pendulum that is there at the lobby is an example of Foucault's pendulum. As the pendulum oscillates back and forth, basically the Earth kind of like rotates out from underneath it. That's the easiest way of thinking of it. This then means that from the surface of the Earth, that non-inertial reference frame, the fictitious force that we then see, it pushes the pendulum to the side slowly over time. So a French mathematician named Foucault devised this experiment back in the 19th century, and then based upon his measurements of the drift sideways of the pendulum, this then resulted in the first physical detection of the Earth's rotation. You are, of course, never going to feel this with your senses because the Earth's rotation, as I said, is rather slight, but it is physically detectable. Okay, let me now go ahead and erase all of this, and then let's get back to the problem. Okay, I'm going to redraw the force diagram from the non-inertial reference frame. So let me rewrite that here. This is getting back to the non-inertial reference frame. Okay, and then we had the following forces. We had, first of all, the force of gravity. We had static friction at its maximum value. Okay, we've got the normal force like so, and then the centrifugal force, the fictitious force from this non-inertial point of view, pointing in this direction like so. Okay, now what we're going to do is use F equals ma here to add up the forces. In order to do so, however, let me ask you this. Once again, for those of you that have ridden this ride, from your point of view inside of the ride, what is your acceleration? Think of it this way. You're looking at other people in the room, and they're all plastered up against the wall like so. Essentially, according to you, what are all of those people's acceleration equal to? 0. Everybody is just standing still according to you inside the ride. So according to you inside the ride, the acceleration is equal to 0, and then therefore all the forces cancel out. Watch what happens now when I add up the forces. So vertically, the forces cancel out. We have Fs max is equal to mg. But then horizontally, the forces cancel out as well. So the centrifugal force is equal to the normal force. But from the top board, we already know what the normal force is equal to. It's equal to ma from the inertial reference frame. It's equal to the net force. It's equal to mv squared over r. This is kind of like how it always works out mathematically, by the way, from the non-inertial reference frame. That is, the amount of fictitious force that you feel from that non-inertial reference frame is equal to ma from the inertial reference frame on the top board. So suffice it to say, when you're inside of the ride, the amount of fictitious force you feel throwing you away from the center of the circle, it's equal to your mass multiplied by your actual acceleration as you then rotate through the ride. This is also the case for those car scenarios from earlier. So if the car is initially at rest and then it starts to accelerate forwards, you feel the fictitious force pull you backwards. The amount of fictitious force that you feel pulling you backwards is equal to your mass multiplied by the acceleration of the car. Ultimately, however, I do end up with the same set of equations here for the non-inertial reference frame as I do on the top board for the inertial reference frame. What this means is that technically you could actually set up any situation in dynamics from either the inertial reference frame or the non-inertial reference frame and ultimately arrive at the exact same equations and then therefore be able to solve for whatever it is that you're looking for. Usually, however, more times than not, we usually set up situations as we've been doing from the inertial reference frame on the top board. And the reason for that is because sometimes from the non-inertial reference frame, the fictitious forces are rather difficult to discern. Sometimes they're a little bit hard to identify. So for that reason, we usually set up situations as we've done on the top board from the inertial reference frame. And I'm using this example here to give you some context, introduce you to the idea of fictitious forces such as the centrifugal force, and also the fictitious force that we feel here at the surface of the Earth as the Earth rotates. Okay, let me go ahead now and get back to the problem itself. Let's just go ahead and complete the example. I'm going to go back to the inertial reference frame to do so up on the top board. Okay, so getting back to the picture as it is up here on the top board, ultimately what we're going to solve for here is the period, and then lastly we'll calculate the amount of G's that you feel as you rotate through the ride. Okay, so getting back to our expressions here for F equals ma, I'm now going to start to combine the expressions together. So in the first expression on the left-hand side, we have Fs max, which is the coefficient multiplied by the normal force like so. Now let's go ahead and substitute the following in for the normal force into the expression right here. Like so. And then somewhat counterintuitively, notice that the mass of the person cancels out. So for those of you that have ridden this ride before, your mass actually has nothing to do with respect to whether or not you're going to start to slip down the wall or be stuck to the wall. Instead, what does matter is basically how quickly you are rotating through the ride, the size of the cylinder itself, and the coefficient of static friction between your body and the wall behind you. That's what's important, not your mass. Okay, now let me go ahead and make the following substitution for the speed v. The speed v is equal to the circumference of the circle divided by the period, and the period, of course, is what we're asked to calculate here in the example. All right, so going back to this step here on the top board, I now have coefficient, and then multiplied by v squared over r. So take each of these terms here, square them, and divide by a radius. When you do the math here, you end up with this expression like so. And this then equals g here on the other side of the expression. Okay, and now what we're supposed to solve for is the period here. So let's just go ahead and cross multiply these guys. So t squared is going to be coefficient 4 pi squared r over g like so. And now last thing to do is just take the square root of both sides. All right, so the period then ends up being equal to the following. Like so, let me just double check my math there, take the square root of that. Yeah, like so, and now let's go ahead and plug in. All right, keep in mind that as we finish the example here, as I said at the beginning of the problem, all the numbers that you're seeing here in this problem, they're typical of a ride such as this. Okay, 2 times pi, and then multiplied by the square root, there we go, of the following, 0.6 times the radius of 1.5, and then divided by g. Take the square root of all of that, and it's about 1.9 seconds, like so. Okay, then let's go ahead and calculate the amount of g's that a rider feels inside the ride. In other words, how many 9.8 meters per second squared of acceleration does the person feel? This will also give you an indication as to why a ride such as this is rather uncomfortable. So what do I need to calculate then for the last portion of the problem? Okay, well, for the last portion of the problem, what we have to do is calculate the acceleration. V squared over r. We'll get that number and then we'll compare it to 9.8 meters per second squared. Now, in order to calculate this number, I'm going to go ahead and make the following substitution here. Once again, it's in the numerator. Square all the terms here and then cancel out by a radius. So when you do, you get this expression here. Now let's go ahead and calculate this in terms of meters per second squared. So I still have the period here, capital T, in my calculator. So let me do that first. I'm going to square that. Take the reciprocal. Okay, and then times 4 times pi squared, and then times the radius. Okay, and this comes out to be 16.33 meters per second squared. And then therefore the number of g's of acceleration, the phrase g force, by the way, is somewhat of a misnomer. The amount of g's is how many 9.8s do you feel? So what I'm going to do is I'm going to take 16.33 and divide it by 9.8. All the units will cancel out. This is a dimensionless quantity. And this comes out to be about 1.67 g's, as we said, like so. So then therefore the amount of fictitious force that you feel when you're inside the ride, throwing you away from the center of the circle, is 1.67 times your weight. So it's as if somebody who weighs 1.67 times as much of you is basically distributed evenly on your body, throwing you away from the center of the circle. So that's the reason why a ride such as this is rather uncomfortable if you've ever been on this ride before. So usually what they do at this ride is that you walk into the room, you stand up against the wall, they spin you up the uniform circular motion, the floor drops, and then they basically leave you there for maybe like 15 seconds or so. And then the floor comes back up again, and then they slow back down the rest, and then ultimately the ride is over. Rides such as this that occur, for example, in carnivals in particular, are what I refer to as barf rides, because they're usually not very large, so then therefore basically what they do is they throw you around in some manner, like the tilt-a-whirl ride and so on and so forth, or the bobsleds or something like that. Basically rides like that, which occur on a small scale, are designed to throw you around and give you certain amounts of acceleration. There is a portion, by the way, of the ride Goliath, that Magic Mountain roller coaster, where when you go through the helical portion of the track like so, you're getting about 4.5 Gs. That's actually pretty excessive for a roller coaster, and you get about 4.5 Gs for maybe about 20 seconds or so. That's a lot. Something like that is kind of towing the line between what's fun and what's actually dangerous. Here's an idea as to what exactly is meant by dangerous. Imagine, for example, high G turns that are executed by fighter pilots. When they do, some of those high G turns that they execute are pulling for them about 9 Gs or so. Ultimately, what keeps a pilot from passing out under those conditions? Well, number one, they don't make those high G turns for very long, just a couple of seconds. And also, when they do execute those turns, in their flight suits, the suits that the pilots are wearing, there are bladders of water that are positioned at different points along their body, such that when they get plastered up against their seat when they're executing those turns, basically those bladders of water, they then push on their blood vessels that try to keep the blood up to their brain as much as possible, thereby preventing them from passing out. So if you've ever been on that ride Goliath at Magic Mountain and you kind of felt yourself start to go gray a little bit as you were going through the helix, it's because blood was not being forced up to your brain enough, and it should be. So just be careful when you ride a roller coaster such as this. Okay, I'm going to go ahead and conclude this video here.